We'll quickly examine different sensor sizes as the concept does appear in 3D graphics software since it's relevant to determining field of view. The standard among professional photographers is the 35mm full-frame sensor, named for the size of film historically used in photography. A 35mm sensor actually has the horizontal and vertical dimensions of 36mm for the horizontal and 24mm on the vertical. All right, so that is important to keep in mind, especially when we're doing our field of view calculations. Cheaper and more entry-level cameras commonly use what are called APS-C sensors, otherwise known as cropped frame, really just because they are significantly smaller than full-frame sensors at around 22 to 23mm in width. The exact size does vary between manufacturers. And all this means is that at the same focal length, the APS-C sensor is going to simply capture less of the scene than the full-frame sensor will, right? That's why it's called cropped frame. Next, we'll briefly go over how lens apertures work in a physical camera. The lens aperture is the opening which lets light into the camera and therefore controls how much light will eventually reach the sensor. Again, in computer graphics, we aren't actually simulating light interacting with a sensor. However, a basic understanding of a physical aperture is still important as it impacts depth of field, something which we'll be simulating later on with our 3D renders. Physical apertures also impact the exposure and sharpness of an image, two things which we won't discuss here. In a physical lens, the aperture is described using f-numbers, or f-stops, defined as the focal length divided by the diameter of the lens's entrance pupil. So in other words, if we rearrange the equation to solve for the pupil diameter, which is the most intuitive measurement of the aperture opening, we'll find that an f number of 4, which will be written as f over 4, with a focal length of 50 millimeters, would give us a lens pupil diameter of 12.5 millimeters. Therefore, because of the inversely proportional relationship between the f number and the diameter of the pupil, or in other words, how much light it's able to let in, we can see that the smaller the f number, the larger the pupil diameter is, and therefore, of course, the more light gets let in. Finally, we'll discuss focus and how it works in a physical camera. Again, in 3D graphics, because of how images are rendered, every visual element will be in perfect focus and the image will appear to be perfectly sharp. So to achieve a realistic result, at least in terms of how human eyes see and how cameras capture images, we're going to need to simulate the idea of focus and have certain parts of the images nice and sharp and perform some sort of defocusing on other parts of the image. And we'll explore how we do this in 3D graphics a bit later on in the course. For now, we'll just explore the general idea of how this works in a physical camera. In the diagrams we've been using so far, we've assumed that the camera assembly is at precisely the right distance from the subject, such that light rays, once they pass through the lens, will converge precisely on the image plane. So we've been imagining something like this, where maybe light coming from some particular point in the scene is going to, once it's refracted through the lens, is going to converge precisely on this image plane. In reality, however, there's actually an imaginary plane at some distance from the camera. There's this imaginary plane in the scene at which light rays reflected off of objects at precisely this distance will appear to be perfectly focused when they land on the image plane. Now, any object slightly in front of or even behind that image plane are also going to be reflecting rays of light, and well, these ones are also going to enter the camera assembly and get refracted through the lens. However, they're going to converge at a different point. All right, so here we can see with this object slightly closer to the camera than the other one we were observing, we can see that the light rays coming from this object actually converge, in this case, behind the image plane. And something that's important to note is if we were to take a look at our image plane in 3 dimensions here, and imagine these light rays coming in and converging behind the image plane, we would notice that they form a circle on the image plane, right? All of the light rays, as they come in, they're going to actually land in this circular shape. So this idea is very important to keep in mind as we move forward here. And of course, even for objects that are perfectly in focus, well, nothing in reality is absolutely 100% perfect. So again, even this point of convergence here, well, there will be some sort of circular shape formed by the light rays as they are projected onto that image plane. So the goal of focusing is to get the appropriate light rays observed from a scene, right? Maybe from this plane right here. The goal is to get the smallest circles, if you will, when those light rays pass through the image plane, thus achieving the best focus possible on objects at, well, this particular distance from the camera. The largest acceptable circle that can be projected onto the image plane that we will consider to be in focus is called the circle of confusion. And the diameter of these circles can vary between different camera sensors. But again, the idea is still the same. It's just the most defocused light rays can be and still appear to be focused well enough when captured by a particular image sensor. So from this understanding of focus, it's fairly intuitive to understand focus as actually a range that extends both in front of the focal plane as well as behind it as well. All right, and the how sharp images are going to be when observed from different points inside this range here, it's going to vary from being perfectly in focus, right on the focal plane, which of course is infinitely thin, so nothing in reality is perfectly in focus, and it's going to get more and more blurry as we either get too close to the camera or too far away. So this area is called the depth of field. It's actually interesting to note that the closer you focus, the narrower your depth of field is going to be, right? So maybe that would, if we were focusing only this short distance here, our image plane would be right around here, and we'd have a very, very narrow, or what we call a shallow depth of field. And on the other hand, the farther away we focus, the wider the depth of field is going to be, right? So I'm kind of running out of space here, but the farther away in the scene that we focus, the wider the resulting depth of field is going to be. Depth of field will be discussed in greater detail later in the course when we discover how it can be simulated on a rendered image. For now, we'll just generalize and say that given a distance to the subject, right? So some distance, the focal length, which is going to be, right, of course, we know what the focal length is. Let's call that F, right? So the distance, the focal length, as well as an aperture. All right, we don't have a lens drawn here, but let's get a different color and just imagine we had a lens here with its opening, which lets light in. So we'll also need a particular aperture, as well as a circle of confusion size, right? And of course, we remember what that is from just a few moments ago. So we'll call that C. So given this information, we can actually determine the closest distance in the scene at which objects will appear to be in acceptable focus, where they're not going to be perfectly focused, But again, because we've got that circle of confusion defined for our particular camera here, we can figure out what is that distance beyond which objects will be in acceptable focus, right? We can also determine the farthest distance at which objects will be in acceptable focus. So these two values are going to become pretty important later on when we discuss depth of field and how we can approach implementing that in 3D graphics.